Hi, Math 117. Miss Griffith here, going over 5.4. We have a new term called a sampling distribution. Anytime you see this term, you are going to have to change the standard deviation. So we're first going to be talking about sampling distributions, what the central limit means, and then how to apply the central limit theorem to find the probability of a sample mean. First things first, what is a sampling distribution? The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. I'm going to refer you to a Party Sabetti video here, but essentially, I could take all of your heights and put them on a dot plot on the board, but we're not there, and it might not look exactly symmetrical. Well, if I did a sampling distribution, meaning let's pretend n equals 4, so I would be taking 4 of your heights and taking the average of that and putting that on the board. Then I would take the next 4 of your heights and putting that average of that height on the board until I do every possible sample of 4 people. Well, that's going to make your curve become more normal. And essentially, when your curve becomes more normal, you have a smaller standard deviation. So that brings us to the central limit theorem. Draw a simple random sample. So anytime you see this, we are going to be changing the standard deviation from size n, okay, or of size n. So in my example, n was 4, all right, from any population with mean mu and finite standard deviation sigma. The central limits theorem says that when n is large, the sampling distribution mean is approximately normal. All right, so here's a population with an unusual shape, but after they did a sampling distribution, so they polled 25 people, and then the next 25 people, and then the next 25 people, over and over and over again until all possible combinations of 25 were sampled, it becomes normal or symmetrical looking. All right, so a sampling distribution is normal if the population distribution is normal, okay, or the central limit theorem applies. The mean is going to be equal to just the mean, all right? So the mean stays the same here if we were to do a sampling distribution. What changes is the standard deviation. So anytime you see sampling distribution or SRS, you're going to know that sigma changes. Sigma is actually going to be the known standard deviation divided by the square root n. So in that last example of that picture you saw, n would have been 25. It's however many you are sampling from the population. So we're going to do 2 examples. One example is just like we've been doing, and then the next example is going to be a simple random sample or a sampling distribution where we're going to have to change sigma. Okay, examples. So this first one you should already be able to do from what we've already done in this chapter. Suppose the distribution of distances that DP students drive to school every day is normal. That's very important, so that means that we are still using our z-score chart, and that is why we were able to use that. Has a mean of 3.2 and a standard deviation of 0.7. This first problem you can already do without any information that we learned today. So number 1, what is the probability that a random student drives further than 4 miles every day? Okay, well, we're first going to need to standardize that if we want to use our z-score chart, right? Because we're going to be looking for z here, and we went further than 4 miles. Okay, well, remember that your z-score is just x minus x bar divided by the standard deviation. And the standard deviation is not changing yet. So in this case, we have 4, because we want greater than 4 miles, minus x bar is 3.2, divided by the standard deviation is 0.7. When we put that into the calculator, you get 1.4286. All right, so our z-score is 1.4286, but we're looking for the area, right, or the probability. So let's first do it with your chart. We're going to look for, I'm going to do 1.43. So in your chart here, we go to 1.43, and we see here's the area. Well, that doesn't really make sense because, I mean, it does make sense, but that's 0.92364. Remember, this gives you the area to the left. So that gave me this area right here is 0.92364. But I'm looking for this area here, okay? So I'm going to have to subtract that from 1. 1 minus 0.92364 equals 0.07636. Again, remember, if you don't want to use your table, you could use normal CDF here in order to find this number. Okay, so on your TI Inspire, you're going to use the normal CDF. It's under distributions. It always asks you 4 things: the lower bound, upper bound, mu, and sigma. Well, here our lower bound is going to be the 1.4286. 1.4286. Upper bound, just a big number. I'm going to put 6 nines. Because we've already standardized the z-score, mu is 0 and sigma is 1. So this way, if you do it this way, you're not going to have to subtract from 1 because it knows you want it from the right, or to the right, greater than 4. So to do this, I'm going to do menu, probability, distributions, and let's go to normal CDF. The lower bound is 1.4286. Upper bound, I'm putting 6 nines. Leave mu as 0 and sigma as 1. Oh, looky here. We get 0.07656, and that is what we got with our chart. You see this, you know you are going to need to change the standard deviation. So essentially this is the same problem, but now it's taking an SRS of 10 students, but we still want to find what is the probability that the distance is greater than 4 miles. Okay, but our z-score is going to change here. Why? Because we have a different standard deviation because of this SRS. So I first want to calculate our new standard deviation. All you do here is take the previous standard deviation and divide it by the square root of n. And n is 10 here. When you put that in the calculator, you get 0.221359. Well, now we can recalculate our z-score. So z is going to still be 4 because we want greater than 4 miles, minus our x bar doesn't change, so minus 3.2, divided by this new standard deviation, 0.221359. This comes out to be 3.61404. Let's look on our chart for 3.6, remembering that it gives us to the left of the z-score. So 3.61 looks like we have 0.99985. Well, that's this area right here, 0.99985. That's to the left of the z-score we just found. Well, we want it to the right of the z-score, so I just have to do 1 minus 0.99985 to get 0.00015 is our answer here. You can also do this with your TI Inspire, your normal CDF. Your lower bound is our new z-score, 3.61. Your upper bound is a big number. I'm just going to be putting 6 nines. And mu, because we standardized this, is 0, and sigma is 1. If you do put this into your calculator, you will get the same thing, 0.00151.